The history of the invention of superior materials is filled with accidental discoveries and serendipity. This is the way that penicillin, Teflon, Post-it adhesive, and many other superior materials were actually discovered. But there is another way, one that takes advantage of the incredible advances that have occurred in recent decades in being able to use supercomputers to more accurately calculate the behavior of atoms put together in different ways. Methods to physically put atoms together in different ways with atomic level control, and methods to see with atomic resolution how the atoms in such artificial materials really are arranged and how the electrons in these new artificial materials are moving. This is where our new national user facility called PARADIM, the platform for the accelerated realization, analysis, and discovery of interface materials, comes in.
So welcome to the PARADIM Bulk Crystal Facility, where we are enabling the discovery and preparation of a new generation of quantum materials. What you see here is the world's first and only high-pressure optical floating zone furnace capable of synthesizing materials in supercritical fluids at 300 atmospheres of pressure. This is a remarkable environment that does not exist in nature and is allowing us to prepare the next generation of quantum materials.
One of my favorite instruments in this facility is this induction furnace, which helps bridge the crystal size gap that one typically obtains in academia, where one grows very small crystals, and industry, where one can obtain very, very large crystals.
Here we see the world's first tilting laser diode floating zone furnace, which is one of the key instruments of the PARADIM crystal growth facility. This has 5 lasers in here, and we can tilt the laser beam, and so it allows us to control the profile during the crystal growth. So here we can grow beautiful thermoelectric and piezoelectric materials.
In PARADIM's thin film facility, users can select between a record 62 elements in the periodic table to synthesize the materials they envision by molecular beam epitaxy. To this fully automated molecular beam epitaxy system, angle resolve photoemission spectroscopy and metal organic chemical vapor deposition systems are being added to increase the diversity of heterostructures and enable users to determine the electronic structure of the materials they create. PARADIM's electron microscopy user facility has enabled PARADIM users to investigate two-dimensional materials by scanning transmission electron microscopy with the highest spatial resolution ever achieved on this class of materials.
In addition to building your materials and characterizing your materials with experiments, there is another step that we can provide in PARADIM, that is comparing your structures with the results from theory. When experimentalists and theorists work together, we have a more insightful way of designing and realizing new materials.
PARADIM isn't just about research, it's about people and education at many levels. For undergrads, we offer a 10-week program in the PARADIM facilities. For grad students, postdocs, and faculty, we offer annual summer schools at Cornell and at Johns Hopkins. Through these programs, we're building a new generation of researchers, a community of practitioners who take a team-based approach to materials discovery.
What excites me most about PARADIM is the opportunity to accelerate materials discovery. Superior materials and the technological revolutions they enable are vital to the success and security of our country. Aided by our superb facilities and talented staff, we invite you to become a materials inventor by taking advantage of a new paradigm for materials discovery.
PARADIM is part of an emerging national network of materials innovation platforms made possible by the National Science Foundation.